Hey there, and welcome. Today, we're going to dive into a type of power that's literally all around us, just coiled up and waiting for its moment. We're talking about stretchy energy, or, if you want to get technical, what physicists call elastic potential energy.
Just take a look at a simple spring like this one. Whether you squash it or stretch it, it's basically holding on to a secret. It's storing energy that's just itching to spring back into action. And this isn't just about springs. From a simple rubber band you snap to the massive suspension system in a car, this hidden energy is a fundamental force hiding in plain sight. So, let's get right into it. What exactly is this energy? We're going to break down the core idea behind what makes things snap, bounce, and spring right back into shape. At its heart, it's actually pretty simple. Elastic potential energy is just the energy an object stores when you temporarily mess with its shape. The key words here are stretched or compressed. You're putting work into the object, almost like charging a battery, and the object holds on to that work as potential energy. And once you start looking for it, you see this stuff everywhere. It's in the springs of your mattress, that satisfying snap of a rubber band, the vibration of a guitar string, and even the incredible power stored in an archer's drawn bow. All of these are just holding on to energy, waiting for the right moment to let it go. Now, you might think this is all random, but it's not. This behavior follows a beautifully simple and predictable rule that was figured out hundreds of years ago. Let's take a look at the elegant physics that governs this whole stretchy world. And that rule is called Hooke's law. It's all about something called the restoring force, which is just a fancy way of saying the force the object uses to try and get back to its original, comfy shape. Hooke's law basically says the more you stretch something, the harder it pulls back. It's a perfect linear relationship. Simple as that. And believe it or not, that whole brilliant idea can be boiled down into this one incredibly neat little formula. F equals K times X. Just 3 letters that explain so much about the elastic world all around us. So let's quickly break this down. F is that force pulling back, trying to restore itself. X is just how far you've stretched or squished it. And K? Well, K is the cool part. It's the spring constant. You can think of K as the object's personality. A really high K means it's super stiff, like a car's suspension. A low K means it's pretty flexible and easy to stretch, kind of like a slinky. Okay, so knowing the force is great and all, but how do we make the jump from that pulling force to the actual energy that's being stored? Well, let's unpack that. And this right here is where things get really cool. Because the formula we use for calculating all this energy isn't just some random equation pulled out of a textbook. Nope, it has a beautiful visual origin. Any ideas where it might be hiding? The answer is right here. If you plot the force you're applying on a graph against how far the spring stretches, you get a perfect straight line. And the energy stored? It's simply the area of the triangle under that line. How cool is that? We're using basic geometry to find a fundamental physics formula. And the logic is just so elegant. We start with the simple formula for a triangle's area, right? 1/2 base times height. Well, on our graph, the base is the extension, x, and the height is the force, F. Then we just do a little substitution. We already know from Hooke's law that F is the same as kx, so we swap that in, do a tiny bit of algebra, and boom! We just figured out the energy formula all by ourselves. And here it is, in all its glory. The elastic potential energy, E, equals 1/2 times k times x squared. And pay close attention to that squared part. It means that if you double the distance you stretch a spring, you don't just double the energy, you actually quadruple it. That's a huge deal. All right, the theory is fantastic, but let's make this real. How much energy are we actually talking about in the real world? Let's plug some numbers into our shiny new formula and find out. So here's our setup. We've got a pretty stiff spring. Its K value is 300, and we're going to stretch it by 20 centimeters, which is 0.2 meters. We have our K, we have our X, we are ready to go. All we do is plug those numbers right into the formula. So 1/2 of our spring constant, 300, is 150. Then we square the extension, 0.2, which gets us 0.04. Multiply those two together, and we get our final answer. 6 joules. That's it. That is the actual amount of energy that spring is now holding, just waiting to be converted into motion or sound, or maybe even a little bit of heat the moment it's released. And that brings up a really crucial point. This stored energy doesn't just disappear. When you let go, it transforms. Most of the time, it becomes kinetic energy, the energy of motion. In a perfect world, all of that stored 1/2 kx squared becomes 1/2 mv squared, launching something forward. It's a beautiful conversion.
But, and this is a really big but, there's a catch. This perfect, predictable relationship we've been talking about, it doesn't last forever. Every single elastic object has a breaking point.
Take a look at this graph. See that nice straight line at the beginning? That's our perfect little world where Hooke's law works like a charm. But if you keep pulling, you eventually hit a point where the material gives up and starts to deform permanently. You've gone past its elastic limit. Think about a paperclip you've bent too far. It never really goes back to its original shape, right? That's exactly what's happening here. So the really important thing to remember is that our awesome formula is a model that only works under specific conditions. As long as the object springs back perfectly every time, you're good to go. But the second you stretch it so far that it gets permanently bent out of shape, the math just doesn't apply anymore.
Which leaves us with one final thing to think about. We've seen how this stretchy energy can be stored up and then converted into motion. A bouncing ball is a perfect example of this energy swapping back and forth. But if that's true, why does it eventually stop? What invisible force is stealing a little bit of its energy with every single bounce? That's something to chew on. Thanks for tuning in.